Okay, so section 1.5, Calculus 30, in your textbook is called Velocity and Other Rates of Change. So what we've been talking about the last few sections here, actually most of the class here so far, is about slopes of tangent lines, right? So if we have some sort of function here that looks something like this, and I want to know what the slope of the tangent line is at this point, we know already that we just find, we use the limits. We can use the limits, and we can use Formula 1 or Formula 2 to calculate what the slope would be, right? So that part is practice that we'll have to keep practicing, right? But the application, I want to talk to you about what this slope can actually mean. I've mentioned it before in class, but one of the things is velocity. Now, how does this slope represent velocity? Well, let's say we have a position versus time graph. And so this is position. Let's say it's height. Okay? Height above the ground. And that's height in meters. And this is time. And let's say that's in seconds. So if we have a graph, here's our x-axis and our y-axis. If we have a graph and we want to find the slope of anything, let's back off from the slope of the tangent line. And let's just say we want to find the slope of, we want to find the slope of the line connecting these 2 points right here. And so I'll just draw a nice straight line here if I can. Okay, so between those 2 points. Come on. There we go. Okay. So this is going to give us change in y over change in x. That's going to be the change in meters divided by the change in seconds. Now, what does meters per second make you think of? What is that? What is that a unit for? Change in distance over change in time. Yeah, speed or velocity. Now, I won't get into the difference between speed and velocity because there is a difference between speed and velocity. And anyone taking physics 30 right now? You took it already, and next semester if we get? Okay, so what you'll find is you'll find out the difference between speed and velocity is speed is a non-vector quantity. There's no direction in speed. But velocity indicates a speed and a direction, or a magnitude and a direction. So we won't worry about the difference between speed and velocity. So if you said speed, you're right. If you said velocity, you're right. Now, notice that the slope of any 2 points, even these 2 points, right? We connect those 2 points. The slope is going to be the speed over from this time to this time. Just like this line is going to be the average speed or average velocity from this time to this time. So if we go back now and we say, what does the slope of a tangent line actually represent? Oh boy. The erase function doesn't work very well in this, actually. So let's just redraw this. So let's say, okay, so there's our line, and it's a tangent line there to the curve. So what is this, the slope of this line, going to represent? It's going to be velocity, right? What else can you say about what that slope represents if it's a tangent line? Anybody? Is it going to be the average velocity between two times? Or is it going to be a velocity, it's going to be a velocity at an instant, okay? Or what we call an instantaneous velocity. So just write this down for notes. The slope of a tangent line to a position time graph, so that's what this black line is right here, represents the instantaneous velocity of this particle that's making this graph, okay, that's traveling through space or whatever. It gives us the instantaneous velocity that it's traveling at that instant, all right? So think about it when you're driving in a car, right, your speedometer. If you look down, if you're driving in a car, you look down and it says, 54 kilometers per hour. At the instant that you see that, that's your speed right there, at the instant, right? if you take your average speed for an entire trip, let's say from when when you start your trip, okay, to when you end your trip, that's an average velocity. So you're going to be going 0 sometimes, then you're going to speed up to 100 maybe, then you're going to slow down, then you're going to speed up again, you slow down and stop. So the average, right, over the whole trip. But there is a point, any point on the graph, you are going to be going some sort of velocity. Now, if this point right here, if this was the line, and this was exactly horizontal, what would be the instantaneous velocity at this point? If this was a horizontal line. Okay, good, good guess. Okay, you said the y value. Well, if this was time t, then the height would be this y value, but that would just be the height. So remember, the slope of the line is the velocity at that point. So meters per second, the slope. If the line was horizontal, the slope would be 0. So what this means is that technically at this point, this person or this particle is going 0 meters per second. Now, I don't want to get too far into this. This is getting into we're going to talk about this in calculus, but the main thing is linking these two ideas. Okay, you ready for it? That the slope of the tangent line right here, which we've been calculating using those formulas, right, using the limits, the slope of the tangent line for a position versus time graph is instantaneous velocity. That's what it is. So, if you've got this written down, this is the connection. The slope of the tangent line for a position time graph is the instantaneous velocity. Your textbook on page 36, and it's a car driving example, just like we just talked about. And it says this: if a car is driven on a highway for 3 hours, the total distance covered is 270 kilometers. It's easy to find the average velocity. You just take that total distance and you divide it by the time that is elapsed. So let's say we're driving to Saskatoon or something. From Regina to Saskatoon, okay, I think it's a little less than 270, but it's pretty close. And so if it took us 3 hours to get there, the average speed would be 90 kilometers per hour, 270 divided by 3. Make sense? Okay? And here's the example that we just talked about. If you watch the speedometer, your speed changes quite a bit. And sometimes it'll be 90, but sometimes it'll be less, sometimes it'll be more. And so the instantaneous velocity is the speed at an instant. And on a graph, that's represented by a single point on the graph, right? A single point in time. And so there we have the limit. Now, this one, what they're doing in the textbook here is they're saying, okay, we could guess what the instantaneous velocity would be if we considered 2 points that are very close to one another and we just kind of had a guess, right? So this is what we've done when we've talked about average slope, right? Or average, the slope of a secant line. And so what I want to just move you quickly to here is the fact that we can use our calculus formulas to find out the exact, or see right here, instantaneous velocity. Okay, so let's do that for, let's see, this is the function here. Let me just see if I... So example 2 in your textbook says, the displacement in meters of a particle moving in a straight line is given by. So displacement in meters, that's sort of how far it's gone. So this is a distance. It's given by the function s equals this right here. So copy this out. S equals t squared plus 2t, where t is measured in seconds, so the time is seconds. So we've got displacement meters versus time in seconds. And it says find the velocity of the particle after 3 seconds. So I just want to note that this language here, after 3 seconds, in this textbook and in other places that you might see, that means at the instant after 3 seconds is passed. So it really means at 3 seconds, at the exact mark of 3 seconds, okay, right there. So it doesn't say after, like when, how long after. Some students have asked, what do you mean after 3 seconds? Like what time then? They mean right at 3 seconds, okay? So what we're going to do is we're going to use our limit formula and we're going to use calculus to find the instantaneous velocity by finding the slope of this graph. So it might be a good idea to graph the function as well. Let's just do that quick, clear everything else. And we'll go t, which is x, comma t here, this button right here, squared plus 2t. And we'll graph that. And so this is what it looks like here. Now, time, a negative time doesn't really make sense, does it? So let's just take a look at what we're really interested in. So let's just go like negative 1 here for x. I think we can keep that as 10, but it looks like we can change the y as well. And we'll make it 20. No, we just want to focus on this, so let's just do 4. Let's see what that looks like. Okay. So we'll squish down the x a bit as well, okay? So x max is 4, and actually that y min, let's go back up to the 25 there. There we go. That's a bit better. So we can see everything. So at 3 seconds, 1, 2, 3, see how the particle's moving? So we're going to have a point of tangency right here. We're going to have a slope of this point of tangency line that looks something like that. So it's going to be, we'll just keep that in mind. All right, so Formula 2, somebody asked about Formula 2 from the last assignment, so let's get some more practice at Formula 2. Let's do that. So the limit as h approaches 0 of f of a plus h, just going to write out the formula here, and you should get used to memorizing this as well, minus f of a all over h. We know that a is 3 seconds, right? A is 3. So this is going to be the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. All right, we're gonna substitute all this stuff in here. It might be a good idea to try just to figure out f of 3 right now. So f of 3 is actually 3 squared plus 2 times 3, right? Which is 9 plus 6, or 15. Is that agreed? So that's what's going to go in here. And of course, with f of 3 plus h, it's the 3 plus h that goes in for t. There and there. Right? So let's do that. We will do 3 plus h all squared plus 2 times 3 plus h minus 15 over h. Now, if you have to just sit and look at that, I understand. Just sit and look at that and make sure that you understand what we just did in that step, because that's a huge